Okay. All right. So boundary testing in unit testing, right? Sorry, I don't mean to sound like I'm repeating myself here, but it's kind of important to go through this material as well. So what do we actually have here? What's going on? Well, let me just move that out of the way. Okay. Now, it's an important concept because often in unit testing, this situation comes up where there's what we refer to as a boundary test, right? That is to confirm and verify that we actually do see when there's a change of behavior of our code called for, right? When a change of behavior occurs as a value crosses a boundary, okay? Simple concept, right? Okay, let's talk about when that can happen. These changes of behavior, there's a whole different range of values they could be, or types of situations that we're talking about here, right? It could be that there's a change in a Boolean value, that above a certain value you should get true, or maybe you should get false, or it should flip-flop back and forth between true and false, right? That's a simple change of behavior that can be triggered by a change of a value of some sort, right? Another very common one is an exception is raised. It could be an argument out of range exception, for example, or any other type of exception, okay? Might be thrown, once again, once you cross a given boundary, right? Above or below, well, that depends on the situation. Okay, so that's two different types of situations. Another one is you might change, if you're doing a calculation of some sort, it could be that a factor used as part of that calculation or that evaluation, right, changes when you cross this boundary. You know, I've got an example here. You know, if sales go above $1 million and you're calculating commission for the salespeople, well, maybe the rate, okay, the rate at which they get paid out commissions changes from one value to another, right? That's another example of a change of behavior crossing a given boundary. And so in our unit testing, we want to make sure that it actually happens, that you see that change occurring when you cross the boundary, right? Final example to consider, right? Sometimes we're changing completely the approach. So it's not just a factor used in a calculation, like a percentage or something, but the entire type of evaluation or type of calculation in many cases, right? My example here, right? Perhaps below a certain number of people, a guaranteed number, booking a conference somewhere. Speaking of conferences earlier. So maybe the fees are based on a flat rate up to a certain number. But when you go above that number, then there's a calculation using a price per person or charge per person and so on. So it's a completely different approach to calculating something that gets triggered or put into play because you've crossed a boundary. Well, these are just all examples of situations. You can see why boundary testing is almost inevitably a significant part of any type of unit test for practical applications that you build out in the real world, right? Okay, so let's talk a bit about how we set these up then. So there's a couple things to consider, right? One aspect are the boundary values, the use cases we use, right, to actually establish our tests, okay, to make sure that we're seeing the change as we cross the boundary, right? So, you know, inevitably, I can talk about this till I'm blue in the face, but just about every year, I always get some student that on a test that involves some boundary testing like this, you know, maybe a boundary happens, like, as I said earlier, 100, right? You know, or $1 million in sales, something changes. Well, you know, instead of just going just above or just below, they throw in a value of 10 million. Well, sure, that's above, right? But that's not very useful as a boundary test, okay? Sure, yeah, by definition, it's above or below the boundary, but it needs to be as close as is reasonable to be a reasonable use case or boundary test, right? So how can we decide what is actually reasonable here, okay? Well, it depends a little bit on the kind of values you're utilizing. So simple things like integers, even Booleans and so on, anything that has a distinct value, well, that's easy, right? Nothing to it, right? If it changes from one integer to the next, well, there's no discussion, right? You can simply set the value according to where the change should happen. And if there's distinct values, such as an integer, it makes it very, very easy, right? But that's not always the case in the real world. Often what we're working with are floating point numbers, okay? Even, you know, you might think of a currency technically it is a floating point number, right? You can have fractions of a penny and so on, about times, date time, or time durations, right? How many hours, minutes, seconds, milliseconds, and so on. These are situations where it's not so clear cut as it is with an integer, right? They are trickier. So usually in cases like that, you do end up working, again, modeling the real world here, in terms of a number of significant digits, okay, as a general term. They might not always call it that, but that's really what is reflected in a given situation, right? So for example, if it's currency, you might be calculating everything down, rounding it, so to speak, to the nearest penny, right? Or you might decide, well, no, we need more accuracy. We're going to go to, a hundredth of a penny or a thousandth of a penny, right? Whatever the significant digits are that you're working with, okay? So here is the general rule of thumb that we usually follow. Now, this might change. In some circumstances, it might be necessary to do something different, or you might be told by whoever's in charge of the project to use a different value. But if you're not given anything else, this rule of thumb is a good one to fall back on. That is to go to 1/10 of whatever the significant digits are, right? So again, if we're calculating currency, just the nearest penny, right? We aren't worrying about fractions of a penny. We're rounding it to the nearest penny and so on. Then if you're looking for a change of behavior, again, let's maybe use that example of $100, right? Then, look for 1/10 of a penny. That would be how you define the upper and lower boundary. Now, which is which, that will actually be specific to the situation. So just remember that as a rule of thumb, go to 1/10 or move an extra decimal place over. That's one way to put it, in terms of whatever the significant digits are, right? And that should help you decide, okay, what are the actual boundaries to use. So just to look at some examples. As I said, integers, hey, they're so easy, nothing to it, right? Even in the homework that I've assigned for you to do, and hopefully everyone's had a chance to get that done because you had lots of time last week, right? We had this was right out of the assignment, right? So for example, in our Willy hand, you're looking at card value. So a king is the value of 13. So if somebody gives your class the value 14 for a card value, well, then we should raise an exception. Couldn't be easier than that, okay? So the two values to use, because that's what it comes down to, is you always need to establish a change in behavior across a boundary. You need two tests, one below and one above, so to speak, right? So 13 should pass. We should get a real value calculated. 14, we should get an exception raised, right? As I said, integers are nice and easy and simple. Okay, now let's talk about some other real-world situations that are not quite so straightforward. Generally speaking, whenever we have floating point, or as I said, date times, time durations, whatever, right? Then unless otherwise directed, okay, we'll use our rule of thumb, right? So I have an example here. So suppose there's some change of behavior of a value of 100, okay? And we're working with two significant digits. So, what values are we going to use for our two above and below, so to speak, use cases, okay? Well, if 100 is a valid value, okay, then we would use 100. So how much above it would we go? Well, if we're going to two significant digits, okay, that would be 0.01. Then we'll just add one more zero. We'll go to 1/10 of that. So by default, our next use case would be 100.001, right? So if on the test, in a situation like this, if you used 1,000, sure, well, that's above, right? That's above the boundary where we expect our change of behavior, but you will not get full marks. In fact, probably not get any marks for that answer, because no, that's not a good boundary test, because you're not establishing the change of behavior actually reasonably at the boundary where things should change. Hopefully that clarifies things a little bit, because maybe this year will be the first time ever I don't get anybody submitting a test with that kind of mistake made. Yay, that'd be great. Now, one final thing to talk about. Up till now, we've been talking about choosing the values for our use cases, right? But whenever we're working with floating point numbers, something else we need to be cognizant or aware of is the fact that there are rounding errors, okay? In all computers, calculators, whatever you want to, use, that's why we have significant digits and so on. There are rounding errors, okay? And that is always a possibility. So how do we handle that if we're not talking about setting up the tests, but actually evaluating? Does this expected result match the actual result we got? Well, if there's a possibility of rounding errors, that is not quite straightforward. Fortunately, they've thought of that. And right in the MS test environment, okay, when we do our Assert.AreEqual, okay, one of the overloads that you might have even noticed yourself is that we can actually pass a delta, right? Delta, fancy Greek word for difference, okay? So if, okay, again, if you're looking for the actual matches an expected value, but there could be a little bit of wiggle room and you're still going to call it a pass, okay, then you get to specify a delta. Rule of thumb, once again, is the same, 1/10 of significant digits. So in my little screenshot here, okay, I would expect it would be 0.001, okay, was the significant digit, so we add an extra zero in front, okay, and then that would be a reasonable delta to say, we're confident that as far as we're concerned, this actual value matches the expected value, right? Okay.